Hi, my name is Jeremy Cowan. I'm a principal SA for containers, and today I'm going to be talking to you about container best practices or security best practices for Amazon's Elastic Kubernetes service. And as part of today's talk, I'm going to begin by talking about how you solve a problem like containers. For those of you who are fans of musicals, you'll know where that reference comes from. We'll then have a look at the shared responsibility model for EKS and its importance, along with a set of security pillars that we've established to help customers secure their containerized environments. And then we'll have a look at the security best practices themselves, beginning with host security, and then looking at the container images, along with identity and access management, network security, pod and runtime security, and then finally auditing and forensics. And then finally, I'll leave you with a few closing thoughts. So let's have a look at the challenges that are posed by containers. Unlike a virtual machine where you're virtualizing the x86 instruction set and running a full operating system, containers are processes that are running on a shared kernel. And isolation is implemented through Linux namespaces and C groups. And while these provide isolation between containers, they're not really considered a strong security boundary. With the proper know-how, you can escape from these namespaces and gain access to the underlying host. So it's important to implement safeguards to prevent that from happening. We'll have a look at those as part of our best practices. Another challenge posed by containers is their relatively short lifespan. Because containers are replaced fairly frequently, it may be difficult to do forensics, particularly if the compromised container has been replaced. Another challenge that's posed by containers is that a lot of traditional or legacy security software is simply not container aware, and this includes things like firewalls and IDS and IPS systems and data leakage prevention systems and so forth. And all of this together really warrants a different approach to security. All right, let's have a look at the shared responsibility model. So it's important to recognize where the line of demarcation is between the things that the provider is responsible for and the things that you as a consumer of the managed service are responsible for. And with EKS, AWS is always responsible for the management of the control plane. The control plane is comprised of a variety of different components, including etcd, the scheduler, the controller, API server. All of that is managed by AWS. And when you use self-managed workers, you're responsible for the lion's share of the infrastructure here, in that you have to manage the worker nodes. And those worker nodes have an operating system. They have an agent known as the kubelet, along with the container runtime, which happens to be Docker today. If there are updates available for those components, you are responsible for patching them. And then similarly, you are also responsible for scaling your cluster when it's warranted. When you adopt managed node groups, AWS assumes additional responsibility. So all of that patching and updating that I spoke of earlier with self-managed workers is now handled by AWS, in that AWS will publish a new version of the AMI that has the latest patches and updates, and you can call an API to orchestrate the replacement of those worker nodes. And you can actually have a mix of both managed and unmanaged workers in your clusters. But with managed workers, you're still responsible for the worker node scaling and the cluster configuration, which, as you can see, is comprised of a variety of different things like horizontal pod autoscaling policies and quotas and limit ranges, RBAC bindings, network policies, and so on. Now with Fargate, we introduce another layer of abstraction where you don't have to manage the infrastructure on which your pods run. That's all handled by AWS, including the worker node scaling. So all that patching and updating and the cluster scaling, all of that is now handled by AWS, and you are essentially responsible for the cluster configuration when you use Fargate. All right, now let's have a look at the security pillars. And when we consult with customers, we try to have this all-encompassing approach that emphasizes the shared responsibility model, which I spent the last couple of minutes telling you about. We also encourage having a cloud-native approach to security, which emphasizes DevSecOps. And all of this has been encapsulated in a set of epics. We have a set of 5 core security epics, which consist of identity access management, logging and monitoring, infrastructure security, and data protection, along with incident response. And then those are complemented by an additional 5 epics, which we complete once we're done with the other sprints. And during these engagements with customers, we always emphasize a defense in depth approach to security, where you implement different controls at different layers of the stack, beginning with the user data, and then moving on to the configuration, the source code, any dependencies, the container itself, and then lastly the host. And we'll actually have a look at a lot of these different layers here as we talk about the best practices for security. Beginning with host security. So the first thing that we recommend is to use an operating system that has been optimized for running containers. As part of the service, AWS offers an EKS optimized AMI. It's based on Amazon Linux 2. But there are other options available, such as BottleRocket, which is an operating system from AWS that is currently in preview, that was built with a security-first mentality. It is optimized for running containers. It has a read-only root file system, makes use of SE Linux, and has several other security features that make it a very secure operating system for running containers, and decreases the likelihood of a process escaping from those namespaces that I spoke of and gaining access to the host, or getting access to other containers running on that host. There are other similar types of operating systems, such as Rancher OS and Flatcar Linux, that could also be used here. The next recommendation is to deploy your worker nodes onto private subnets. Of course, there may be exceptions to that where you have to deploy your worker nodes onto a public subnet, but generally speaking, you should deploy your workers onto private subnets and route traffic to those worker nodes through, say, a public-facing application load balancer. The next recommendation is to run Amazon Inspector or a similar type of agent to continually assess alignment with best practices and compliance requirements. There are a couple of tools available to help you with this, including a tool from AquaSec or Aqua Security known as KubeBench, which looks at the configuration of the kubelet and assesses its alignment with the EKS CIS benchmarks, which were recently published. And there's a link here in this slide to a blog post that has additional information about that. You should, of course, minimize and audit access to your worker nodes. A good way to do that is by using SSM, because with SSM, not only can you control access to those hosts through IAM, but you also have the ability to audit access through CloudTrail. And then finally, if it's warranted, you may want to consider using SE Linux, which can be used with Red Hat or CentOS. And for those of you who aren't accustomed to writing SE Linux policies, There are several tools available, such as Audit to Allow, Audit to Why, and SE Alert that can help you do that. Next, we come to securing container images. First thing that we recommend doing here is to scan your container images, and there are a lot of really good open source solutions for doing this, including Anchor, Claire, and Trivy. We actually make use of Claire as part of ECR's scanning. ECR is our Elastic Container Registry, and you can scan an image on push or on demand. But beyond that, it's always a good idea to create a slim image, starting with a slim base layer. So you can use an image like Alpine, or if you're using a runtime like Go, you can make use of the Scratch base layer and reference a static binary, which is extremely secure because there are no extraneous binaries in the image other than your application. Another recommendation is to defang your images. And you can do this by removing files with the setUID or setGID bits from the image. And there's actually a line that you can add to your Docker files to find and remove or remove these files from your image, or change the setUID and get GID bits. And then similarly, you'll also want to, well, part of the reason for doing that is because you want to prevent escalation of privileges, and with those bits set, you can do that. That's why it's important to remove those files. And then similarly, it's also important to run your application as a non-root user, and you can do this by adding the user declaration to your Docker file. But as part of your CI/CD process, we recommend that you lint the Docker files for the use of that directive, and then possibly failing the build if that directive is or that declaration is missing. You can also use controls within Kubernetes like pod security policies or security context to run an application as a particular user. And then lastly, you'll want to use endpoint policies and private endpoints with the Elastic Container Registry because there is an attack vector where you can package data in an image and then push it to another ECR registry in a different account. And by using an endpoint policy, you can restrict which accounts images can be pushed to. All right, on to identity and access management. There are several general guidelines that you should follow, beginning with practicing the principles of least privilege. This applies to both IAM along with Kubernetes RBAC. You should consider configuring your EKS cluster endpoint to be private. By doing so, you will restrict access to the API endpoint, to the VPC and VPCs that are peered with the cluster VPC. If you like the convenience of being able to administer the cluster from outside the AWS cloud, you can configure the EKS cluster endpoint to be public. But if you do so, we recommend that you create a set of whitelisted IPs that are allowed to access the cluster. And then, of course, you'll want to periodically audit access to the cluster. You can do that by looking at the AWS auth config map, which controls which IAM users or roles have access to the cluster. You can also look at CloudTrail. When it comes to assigning identities to pods, we recommend using IAM roles for service accounts, or IRSA. This is considered safer than, say, storing access key and secret key in a config map and then referencing that in your pod manifest. This works with newer versions of our SDKs. If you have older versions of the SDKs that you can't upgrade, there are a couple of open source solutions that you could potentially use here, like kube.im or KIAM. But we advocate using IRSA because it is a supported solution from AWS. And then if you are going to assign identities to pods, we recommend blocking access to EC2 metadata because pods that run on a host will by default inherit the role assigned to that host unless you block access to EC2 metadata. And then from a Kubernetes standpoint, we recommend using different service accounts for each application, particularly if they're going to consume the Kubernetes API. If they're not, then you can potentially consider disabling mounting of the default service account token, because there's really no need for the application to call the API, and therefore they don't need a service account token mounted to it. All right, when it comes to network security, it's really important to realize that by default, all traffic between pods within a cluster is allowed. And so we recommend restricting that traffic, and to do so, you can make use of network policies. Network policies are really great for restricting east-west traffic within the cluster, or between applications that run within the cluster, although they can be used for north-south traffic. When you run Kubernetes within AWS, you do have other options available for that. For example, you can use security groups, but you can still use network policies here for north-south. When you do use network policies, we recommend beginning with a deny all global policy and then incrementally adding policies that provide greater freedom of traffic between applications. The first rule that you probably want to create after creating that deny all rule is a rule that allows port 53 or DNS egress to the kube system namespace. This is where core DNS resides, and so for service discovery, you really need to allow that sort of traffic into kube system. And then if you are deploying multiple applications into a namespace and they have a need to communicate with each other, the next rule that you'll likely want to create is a rule that allows all traffic within a namespace. And then if warranted, you can create more permissive rules from there. It is a good idea to restrict outbound traffic from pods that don't need to connect with external services. However, if you do have applications that run within your cluster that have to communicate with services outside the cluster, you can implement that through Cilium. Cilium is another network policy agent that you can use with EKS. And Cilium has support for layer 7 policies where you can actually reference a DNS hostname. And so you can reference the hostname of, say, an RDS database here. Another option that will be available relatively soon is this ability to assign a security group to a pod. And so with that, you'll be able to secure or control the traffic between services within the cluster and services that run within your VPC. And then finally, we recommend using an encryption for service-to-service traffic using a mesh. Although a mesh really isn't the only option here, there are a variety of reasons for implementing a mesh besides encrypting network traffic. For example, it gives you better observability, and it gives you lots of different options for routing traffic, including things like backoffs, retries, circuit breaking, practicing chaos engineering, and so forth. But if you're strictly looking at network encryption, you can implement that through a select set of CNI plugins, such as WeaveNet, and Nitro instances. So there are a handful of Nitro instances that encrypt network traffic by default. So all traffic between these instances are encrypted with TLS. When it comes to pod and runtime security, we recommend using PSPs or the open policy agent with the Gatekeeper admission controller to implement the following runtime security measures. They include things like denying privileged escalation, denying running as root, denying mounting host path, and dropping Linux capabilities. And these are really considered table stakes. They'll help you mitigate the risk of an attacker escaping the confines of a pod or a container and getting access to the host. Of course, you will need to grant exceptions for certain applications or agents that run within your cluster. For instance, a lot of security agents need to run as privileged, and logging agents need to mount a host path. But for applications that don't, which is a majority of them, it's a good idea to have these rules applied to them. If you require additional controls, you can complement your PSPs with AppArmor or SecComp profiles. This is a little challenging to implement because you have to distribute those profiles yourself onto the nodes and then reference them in your pod security policies. But they do offer an additional layer of protection. And then there are a lot of really good third-party options available here for runtime security, including those from Aqua and StackRox, Sysdig Falco, which is an open source solution that's now part of the CNCF, and Twistlock. All of these have really good solutions for runtime security. And finally, on to auditing and forensics. So the first thing we recommend doing here is to enable the control plane logs. This will send logs for the controller manager and the scheduler, along with the audit log and the API, to CloudWatch. And you could use CloudWatch logs or log insights to analyze those logs. Similarly, you can stream your logs from your containers to an external log aggregator, be it CloudWatch or Elasticsearch or a different backend altogether. It's a good idea to audit the Kubernetes control plane and CloudTrail logs for suspicious activities. There are a variety of queries that you can issue against the logs that I mentioned that will show you whether a particular API call was allowed and why it was allowed. I'll talk about this a little later when we get to the Security Best Practices Guide. And then if you do suspect that your pod has been compromised, the first thing that you should do is remove or change the labels of the pod and create a network policy to isolate that pod from other pods. By changing or removing its labels, you effectively remove it from the deployment and replica set that it was originally part of, so that it can be managed separately from the rest of the pods. And then if you suspect that the node has been compromised, you'll want to coordinate that instance and potentially isolate it from the rest of the worker nodes. Once it is isolated, you can then remote into that system and use different tools to capture volatile artifacts on that node, such as its memory and disk. There is a really good solution an open source solution that was built by Intuit, known as Kubeforensics, and I have a link down here, which will help automate the capture of the container state. And now on to the closing thoughts. So it's important to emphasize here that security is really everyone's responsibility. You can't simply offload this to the security team. Everybody is really accountable for ensuring the security of the environment. Part of that is adopting this DevSecOps mentality, and that involves shifting left, which is this idea where you're implementing these controls and mitigating risk earlier in the release cycle, so that you're not waiting until there's an issue in production to realize that you think things have been misconfigured. You can capture those earlier, give feedback earlier, and correct problems before they become significant issues. And then another really important thing here is to understand the shared responsibility model. So knowing where that line of demarcation is, what you're accountable for, and what the service provider is handling. And as I referenced before, we do have a security best practices guide. A lot of the things that I've told you about today are captured in this guide. A link to the guide is down below, and we encourage feedback, or if you happen to feel like there's a best practice that's missing from the guide, we definitely encourage you to submit a pull request. We don't have a monopoly on ideas, so if you have a best practice that you'd like to share with the rest of the community, please submit a pull request. And with that, I'd like to thank you for your time and enjoy the rest of the conference.